Hello, we're going to have a look at complex conjugates in this video. It's the second video in the complex playlist, and if you don't already know what a complex number is, then you might find it useful to watch the first video, just give a little introduction to them. So let's start off by reminding ourselves of a complex number. So normally we use Z to represent a complex number, and we write it in the form A plus BI. If you remember, A is your real part and B is your imaginary part, because a complex number is made up of both real and imaginary. Now, a conjugate is a complex number that is incredibly similar to any given one, with the difference of the sign in the middle being a negative, or the opposite sign. And the way that we denote a conjugate is to use a little asterisk or star, so Z star. So we're going to have exactly the same real part, but the opposite sign of the imaginary part. And you're potentially going to recognize this kind of setup. There's two things you might recognize here. One, you might be thinking things like difference of two squares, because it has that setup. Also, you might be thinking about what we do when we're rationalizing the denominator with something like 3 plus root 2, and we have to times the top and the bottom by 3 minus root 2. So these are both good things to be thinking about, because they are techniques that we're going to be using in the video today. So I just want to run through some useful things that happen when you work with conjugates. If we add them together, so we're taking two complex numbers, and if they are conjugates and we add them, what happens? So we're going to get A plus BI plus A minus BI, and quite nicely the imaginary parts cancel out and we end up with 2A, which we would note is a real number. So the sum of two conjugates is real. And what happens when we multiply them? And this is where that difference of two squares idea is going to come in. So write these brackets down first. So we take our complex number, we take our conjugate, and let's expand. So we are going to get A squared. And if we apply difference of two squares straight to it, rather than worrying about multiplying out every single term, so that's going to be A squared minus B squared I squared. And then we remember that I squared is -1, because I represents the square root of -1, which actually turns this into an A squared plus B squared. So when you're working with complex numbers, rather than the difference of two squares, we actually have the sum of two squares. And this is also real. Okay, so we've got this complex conjugate pair. Let's actually make a note of that. This is a complex conjugate pair. And there's going to be two things we're going to apply this to in the video today. First of all, we're going to look at how, when you have a complex root of a polynomial, so we're going to look at quadratics in particular, then it must come in a pair. So there must be another complex root that has the conjugate set up to the first root that you know about. And we're also going to have a look at the equivalent to rationalizing the denominator, which we're going to call realizing. So we're going to do some realizing of the denominator. But first of all, let's look at the roots of polynomials. To kind of have a mild proof that we are always going to get roots. If we're going to get complex roots, they will always be in conjugate pairs. Let's just have another look at the quadratic formula. And I'm using Z because I know I'm working in complex numbers. So minus B plus or minus the square root of B squared minus 4AC all over 2A. So I'm just going to split apart the bit before the plus minus and the square root after. The square root is the source of our imaginary part of this number, bear in mind. So we're considering this when the discriminant is negative, because we know we're working with at least one complex solution. So if we split this apart, we know that minus b over 2a, that's going to be our real part. Then we're going to have a plus minus. And then now if we know that this is going to be negative, we can take out a factor of -1. So we can actually instead do the square root of 4ac minus b squared, knowing that that can now be found because this is now positive, and then have an I here because we know that we've taken that -1, that root -1 factor out over 2a still. So this shows us that our two roots that we get for our quadratic are going to have the same real part, so it's going to be minus b over 2a every time, and then the imaginary part is going to have the same coefficient of I, except one's going to be positive and one's going to be negative. So that is exactly the setup of a complex conjugate pair. So we're going to look at what happens if we know one root, and the fact that we can find another root, and therefore we can find the quadratic that these two roots came from. Now, before we jump into that, I just want to go for a very small bit of the results of roots of polynomials that is actually going to make our lives a little bit easier in terms of the amount of working we have to do. So if we consider that alpha and beta are the roots of a quadratic, then we should know from things like the factor theorem that z minus alpha and z minus beta are therefore factors of the quadratic in this case. If they're the only roots, it would be a quadratic. That means that the original quadratic that these roots came from must be z squared minus alpha plus beta z plus alpha beta. This basically means then if we know the two roots of a quadratic, then we add them together to get the negative coefficient of z, and we multiply them together to get the constant term on the end. And if you remember from what we did at the beginning of this video, we get quite nice results when we add and multiply complex conjugate pairs, and the two roots of our quadratic will be complex conjugates because they have to be. So we can really utilize this to save ourselves from having to multiply out. So we're going to take the example then that we're going to say if alpha is 5 minus 2i, let's say we know that that is a root, then what is the quadratic that this root came from? Well, straight away we can state that, I'm going to call it alpha star, is also a root. So the conjugate to this number, so we take the same numbers for real and imaginary, but we make the imaginary part the opposite sign. So we know that this is also a root. See, now here we could say, okay, well our quadratic is made from the bracket z minus 5 minus 2i times z minus 5 plus 2i, and then expand, like do the double bracket expansion, which is going to then require expanding these as well. There's quite a bit of work involved there if you're not fully aware of the nice results that we get from this. So we could expand that. I'm not going to do that now though, because it's much more sensible to make use of this result where if you know the two roots you can just simply do these things. So we're going to put or, we can do this. So alpha plus alpha star, so if we sum these conjugate pair roots together, we know we're going to get two lots of the real part, because then the imaginary parts will cancel out. The minus 2i and the plus 2i will cancel out. So that's going to be 5 plus 5, which is 10. And then if we multiply them together, then we know we're going to get the sum of two squares. So it's going to be the 5 squared, which is 25, plus the 2 squared, which is 4. So that's going to be 29. And then we can go straight to writing down the quadratic. So it's always minus the sum, so 10z, and then plus 29. So there's the quadratic that the root 5 minus 2i came from. Okay, so one more thing to do, and that is realizing the denominator. So realizing, so this is just like rationalizing, and it's going to use the same technique. So that's quite nice. It's not anything, you know, massively new to learn. So it will take the example 8 plus I over 3 minus 2i. So, you know, as mathematicians, we don't like having anything remotely strange in our denominators. Don't like negatives there, don't like decimals there, don't like irrational numbers there either. And it's exactly the same for complex numbers. We do not like having complex numbers down here. So we're going to use the technique of the conjugates to remove the imaginary part of the complex number in the denominator. So we're going to multiply, just think about what you do with surds, multiply the top and the bottom by the conjugate of the denominator. So 3 plus 2i and 3 plus 2i on top. Obviously you have to do the same to the top and the bottom. So we know that when we multiply these in the denominator, if we look at our z star product here, we know that we're going to be able to completely eliminate the imaginary part. So let's do the denominator first because that's easier. So that's going to be 9 because it's 3 times 3 plus 4 because it's 2 times 2. You don't have to go through the expansion. If you know that it's going to be sum of two squares, then you can just write it down. Now on the top, we're going to be doing 8 plus I times 3 minus plus 2i. So 8 times 3, 24. Then we'll do plus 16i. Then we've got plus 3i. And then we've got plus 2i squared. So in the numerator there, we'll do the denominator is going to be 13. In the numerator here, we know we're going to have to deal with this I squared. So I squared is -1 again, so that's going to become -2. So that actually becomes 22 for the real part, and then the imaginary part is 19i. So obviously our number is still complex, but crucially, the denominator no longer has an imaginary part to it. We probably would want to write this out with its real and imaginary parts separate. Potentially useful for whatever question we're doing that this is part of. And there you go. We have realized the denominator. So that's going to be it for today's video. We've introduced the concept of conjugate pairs. We've seen how they work with addition and the product. We've seen how they can be used to find more roots and therefore find the polynomial that it comes from. And actually that's going to be applied to more than just quadratic. So the next video in the playlist is going to be all about looking at the possibilities for roots in cubics and quartics. So how many real, how many complex can we possibly get when we raise the order of the polynomial. So look out for that one. And if you found the video helpful, then please leave a like and obviously subscribe to the channel if you'd like to see more. And I will see you in the next one. Bye.